I will talk about my recent work published in Archive in March and soon to appear in JHEP about evaluating Feynman integrals from positivity constraints. I will talk about some background. Then most of my talk will be explaining a simple toy example for one loop bubble integral. And I will show that the method is actually not just a toy eventually by showing you results for evaluating some three-loop integrals. Okay, let's get started. Feynman integrals, that's a very classic problem, as old as quantum field theory itself, but it's also a very active research frontier. It has well-known applications, for example, in Euclidean physics, nuclear physics, statistical mechanics. And in recent years, it's also been applied to fields like gravitational wave physics and cosmology. And so, for example, in the last few years, I've been actively exploring new methods that make predictions for gravitational wave physics using loop amplitudes from quantum field theory. So there are many motivations to improve our abilities to evaluate Feynman integrals. There are, of course, many methods that have been invented over decades. Just read out some names: Feynman parameter integration, Mellon-Barnes representation, differential equations, difference equations, etc. So, and some of the most automated and widely applied numerical methods include sector decomposition, which allow you to evaluate with Monte Carlo integration. And there's also numerical series solution of differential equations, which have been quite active field recently. But they are still, it's fair to say that it's still challenging to evaluate Feynman integrals, especially when you go to high loop orders or a large number of external legs. So new explorations, both on a theoretical level and at a practical and implementation level, that's very much warranted. So I'll suggest a new idea for evaluating Feynman integrals. I think it's a new idea for evaluating Feynman integrals, but not new for in the wider theoretical physics, because it's been very successfully applied to other subfields. Some of which include the conformal bootstrap, S-matrix bootstrap, EFT positivity bounds. What's shared between these fields is that you often can formulate positivity constraints, for example, by imposing the unitarity of some Hilbert space. And you formulate positivity constraints and you solve them. In some of these works, for example, for S-matrix and EFT context, sometimes people have used perturbative calculations to cross-check the results, which beg the question, since these checks involved Feynman integrals, are there positivity properties that exist for the Feynman integrals themselves? And the answer here is yes. The one inspiration of my work comes from recent work in bootstrapping quantum mechanics and lattice models. And so it has, it's actually, there are a few dozen papers on these subjects in the last few years. I think Scott in the audience has also worked on this in the lattice context. In the simplest setting, people have looked at one-dimensional quantum mechanics with some polynomial potential of degree d. So for any eigenstate, any of the energy eigenstates, the unitarity implies that if you insert any operator O and then an O dagger, you expect this expectation value to be greater than or equal to 0. For example, you could consider this operator as an arbitrary polynomial in the position, as well as momentum variables. Now, if you impose the eigenstate condition, that the expectation value of HO is equal to E times O, and then the expectation value of the commutator of H with O is 0 for any energy eigenstate, you will get a set of recursion relations. So if you solve these recursion relations, you can reduce any expectation value of x to the n in the energy eigenstate to linear combinations of a finite set of moments. So this exactly how many moments you need depends on the degree of your potential, depends on this d. But for example, if you are talking about the unharmonic oscillator, which is just the harmonic x squared potential with extra x to the fourth potentials, then you only need an x to the I power with I up to 3. And once a finite set of moments are assumed, any larger moments can be written as can be re-expressed in terms of these first few moments. So if you write down arbitrarily complicated O, and then this expectation value can consider include moments involving high degree polynomials, but all such expressions will turn into inequality constraints on the first few moments, and so you can build up more and more constraints to constrain the first few moments to a very high accuracy. And this essentially allows you to algebraically solve the energy spectrum to a high accuracy. This procedure actually has some interesting analog in Feynman, in the evaluation of Feynman integrals, which is the well-known technique of integration by part reduction. I'll get to this in a bit. So this inspired the new method for evaluating Feynman integrals, which I will explain in detail. So just as an advertisement, I will just characterize this method as the first method based on inequality constraints and the numerical technique of semidefinite programming, both of which have been successfully applied to other subfields in theoretical physics. We have yet to see how practical this method is, given that evaluating Feynman integrals is an extremely research field with many mature methods. But I can say that there are hopeful signs that we are on the right track, as the method can reach a moderately high precision. For example, in the later examples I will show you, I can reach 10-digit precision without too much computation time for a non-trivial 3-loop example. I can handle dimensional regularization, i.e. the epsilon expansion, and the method seems applicable to a wide class of integrals. Now, I will start from a one-loop toy example, but before I proceed, any questions at this point? Okay, let me carry on. So here's the one-loop example. It's a very simple bubble integral with an external massive leg and also internal massive lines with mass m. We will first look at the simplest case, which is the case where p squared smaller than 0. In such cases, it's easy to do a Wick rotation to go from Minkowski space to Euclidean space. Now you get integrals in Euclidean space. Then you can immediately say that the integral has to be positive because the propagator denominators in the Euclidean space-time is always greater than or equal to 0. But can we say something more precise? Not just the integral is greater than 0. Can we actually pin down its value? As we will see, the answer is yes. So I'll first introduce the technique of integration by parts reduction to refine our very crude first statement that the integral is simply greater than 0. Integration by parts is well known in undergraduate calculus. For example, the example of gamma function integrals defined in this way. By integration by parts, where there is no boundary term in this case, you get a recursion relation between such integrals for different integer parameters n. Through this recursion relation, you can express any such integral, for example, gamma 100 or gamma 1000, you can re-express it in terms of gamma of 1, which is the master integral, i.e. the starting point of your recursion relation. For Feynman integrals, there's a very similar story. If you use dimensional regularization, it has a very useful feature that total derivatives integrate to 0, because you can always find a dimension in which the total derivatives vanish at the boundaries, and then you assume your result can be analytically continued to any dimension. So the total derivatives will always be considered to be 0 in dimensional regularization. And specific to the example of the bubble integral, it will be useful to consider the two denominators, each raised to some arbitrary power, a1 and a2. If you set a1 and a2 both to be equal to 1, that's your normal bubble integral, which you write down from Feynman diagrams. If you set one of the indices to 0, so the second propagator is raised to the 0th power, which is just 1. It just means you are throwing away the second propagator. You get an integral with just one propagator. That's simply the tadpole integral. It's just the integral you obtain by shrinking the second propagator to a point. No matter how complicated your integral is, for example, you can have a1 equals 1000, a2 equals 100. It doesn't matter. It will be just some complicated linear combination of these two master integrals with coefficients being rational functions in your kinematic variables p squared, m squared, and your space-time dimension d. For our talk, it's more convenient to switch to an alternative basis. So with a1 equals 2, a2 equals 1, that's an alternative bubble integral, and an alternative tadpole integral where the only surviving propagator is raised to a cubic power, because this gets rid of UV divergences.
Just to make sure I understand the notation, I sub 1, 1 is the integral we want, right?
Yeah, exactly.
Okay, thanks.
Okay. Now I will show you some first results, which I call ad hoc positivity constraints. So the game is just to write down some random integral, which you know to be must be positive, and then see what constraint you get from it. So here I will unfortunately introduce a little bit of more notation just to simplify how I write down things. Row 1 and row 2 will be the two quadratic expressions, will be the two propagators. And now I consider this I2, 2, which is the integral where both row 1 and row 2 are raised to power 2. So so you get something that's quartic instead of the usual quadratic propagator. But still, this integral must be greater than 0 in Euclidean spacetime. By performing IBP reduction, integration by parts, in short, IBP reduction, this turns into the linear combination of one bubble integral I2, 1 and one tadpole integral y I3, 0. And so I know this linear combination is greater than 0. That tells me that the ratio of this bubble to this tadpole integral is greater than some rational function written in terms of the mass and the external momentum squared. Okay, so now I've put a bound on my finite bubble integral. So to go back to Scott's question, what I will actually evaluate directly is this finite bubble integral, but it's related to the original bubble integral I 1, 1 in a very simple manner. So it's essentially the same question. Okay, so this makes our statement sharper than just saying the bubble integral is positive. It actually has to be greater than some specific value. But this is still not good enough because it doesn't. It only gives a lower bound, but not an upper bound. But it turns out that we can also get an upper bound just by writing down a different test integral. Okay, so the previous slide is line 1 here. Now the actual information I add is line 2 here. Now I just try some different integral, which is still positive. So 1 over row 1 and 1 over row 2 are positive expressions. I take the difference, and this is no longer necessarily positive. But if I just square it, then it has to be greater than or equal to 0. And if I integrate over loop momentum space, since it's only 0 at isolated isolated points, then the overall integral it's going to be greater than 0. So if I do my integration by parts reduction again and rewrite this expression as a linear combination of this finite bubble integral and finite tadpole integral, I get a different bound. And here the two integrals actually appear with different signs as opposed to the previous bound. So here I actually get an upper bound. So that's the minimally acceptable result to be shown in the plot. So I have an upper bound and a lower bound plotted as a function of this dimensionless ratio p squared over n squared. You can see that it's actually the result is actually correct, since the exact result, which is in terms of some logarithm for the bubble integral in 4 dimensions, do lie on between our lower bound and upper bound. And so this plot has a curious feature that if you set the external momentum p squared to be 0, and the upper bound and lower bound will converge, and so all the 3 curves will go to the same point. But once you give it a little bit of thought, it's not surprising at all, because the integral only depends on this Lorentz invariant quantity p squared. And if p squared is 0, you can set p equals 0 identically without loss of generality. And if all components of p is 0, this is the two propagators become identical. So the bubble integral become indistinguishable from a tadpole integral with just one propagator, but with this one propagator raised to a higher power. So my two integrals, a bubble and a tadpole, they become the same thing when p goes to 0. So that's exactly as expected. And so that's a nice consistency check that our bounds are behaving nicely. Okay.
Can I ask, this should probably be obvious to me, but on this slide, why does I3 comma 1 not appear? I mean, in line 2, if I expand that, I get 2 times I3 comma 1. How did you get rid of that?
Oh, okay. Yeah, so the short answer is just integration by part reduction. That's the procedure where A1 comma A2 for any positive integers A1 and A2 are rewritten as linear combinations of two master integrals. So you are free to choose the basis of two master integrals. It could be just a simple bubble and a tadpole, or it could be a bubble and a tadpole, each with some propagator raised to a funny power, just to make things a little bit simple, because you get rid of UV divergence. But yeah.
Okay, thanks.
Yeah. So the first example is just I2 comma 2 written as a linear combination of these two master integrals. You get a bound on their ratio, and then you write down something else, you get another bound, which is in a different direction, an upper bound, then you get two-sided bounds already. Okay.
Is there always a unique way to write it in terms of the master integrals?
Yeah, because if you are if you have a minimal basis of master integrals, then there's no because it's actually a basis through which any such integrals can be expressed. That's not immediately obvious, but it's a well-known result in the study of Feynman integrals. Once you fix the set of master integrals, then their coefficients are also fixed for any integral you want to evaluate, because the master integrals are truly a basis.
Okay, thank you.
Okay. So now it's very good that we can get any two-sided bounds, but in 2023, that shouldn't impress you, because if you look at the plots, I've just evaluated the Feynman integrals to something like 50% relative accuracy for a very simple one loop example. But fortunately, we can improve the method, and I'll soon show you how to get to essentially any accuracy you want in this example, as long as far as your computation power allows. And the idea is simple. You need to have more constraints to get your integrals more tightly bounded. To write down the most, so the way I do it is to write down the most general positive integral that can be expressed in this family of bubble integrals. So for some arbitrary reasons that are not so important, I will have a starting power of 2 for one of the propagators. The other propagator is left alone, row 2, not raised to any power. All these expressions are positive. Now I will write down an arbitrary polynomial in 1 over row 1 and 1 over row 2. And I will cut off this polynomial at some finite degree, because I cannot handle infinitely many terms when I have finite computation power. But I can have 1 over rho 1 to some power, 1 over rho 2 to some power. I can also have cross terms, just in any multivariate polynomial. So the polynomial will not have a definite sign, but once I square it, I will have some integral which is positive. Once I expand this polynomial, I will get a sum of monomials. And each monomial will be the integral of 1 over rho 1 to some power times 1 over rho 2 to some power. And in my shorthand notation, that will be written as A1, A2. And as I showed you earlier, by integration by part reduction, all these expressions are completely reduced to linear combinations to the two master integrals. So if I write down such a general polynomial, I can actually get infinitely many constraints, because every monomial in my polynomial can have an arbitrary coefficient. And for such a polynomial with arbitrary monomial coefficients, the final expression is positive because I square the polynomial. And if you notice that this is a quadratic expression in my alpha I parameters, I can write the whole expression as a quadratic form as some alpha vector, which is a column vector of my alpha 1, alpha 2, alpha 3, ... And of the transposed row vector, and then a symmetric matrix sandwiched in between. This symmetric matrix just captures all the coefficients of this polynomial in alpha I. Since I know that this expression is positive semidefinite for any alpha I parameters, I know that the symmetric matrix M is positive semidefinite. Stated in another way by elementary linear algebra, I know that all eigenvalues of this symmetric matrix must be non-negative. This is obvious by proof of contradiction. If any eigenvalue is negative, then you can find an eigenvector alpha which makes this expression negative. And so with this set of alpha I parameters, the integral will be negative, which contradicts our expectation. So you know this symmetric matrix is positive semidefinite, and by integration by parts reduction, every element of the matrix is a linear combination of these two master integrals. So the whole matrix is decomposed into my bubble master integral times some matrix of rational entries plus a tadpole integral times some rational matrix. The tadpole integral is can be trivially evaluated in terms of gamma functions, and so I would take it as a known input. And the bubble integral is easy by the standards of 2023, but for my talk, I will treat it as an unknown parameter. It will be constrained by this matrix relation that this matrix is positive semidefinite. Okay, now I will go to the next slide. And so as I said that we demand every eigenvalue to be.
So, can I ask a question about the previous slide?
Okay.
The very first constraint you mentioned in the talk, I think, was that essentially I10, the integrand in there, as a result of the integrand in there being non-negative, at least for p squared greater than 0.
Right.
That integral has to be non-negative. And a similar thing can be said for, I think, I30, I5, right? Any odd power, but those constraints aren't included in this. Is that correct?
So actually those constraints those simple constraints are actually also included, because, for example, if you set all these alpha parameters, you set alpha 2, alpha 3, alpha 4 to be 0. You just get alpha 1, which is scalar, some number. So you are just saying that this integral itself is greater than 0. That's I2, 1. So those simple integrals are also, those simple constraints are also special cases of this more complicated constraints.
Wait, sorry, I'm not seeing that. So I think I have to square.
I think it's just because I put some minimum starting powers here. There's a 2 and there's a 1. But for example, so suppose okay. You are right about something. For example, I can get 1 over rho 2 squared if I square this term, but I cannot get 1 over rho 2. So there's some odd even division. So I'm missing half the constraints. Yeah, you are right.
Like
about
I5 comma 3, for instance, I think you're missing. And I think that doesn't matter, right? And you still get precise results even if you're throwing away these constraints, and so you decide not to care.
Yeah, that's right. You can actually include them. For example, because there's an odd even gradient here, you can write down another equation like this, but starting with power like 2 and 2, or with power 1 and 1. So yeah, you can just write down another equation to include all those constraints. But the improving accuracy from this is insignificant compared with the improvement in accuracy as you successfully push up the cutoff degree. So it doesn't matter that much, but yeah, but it can help.
Gotcha. Thanks.
Okay, that's a very good question. Now I will just plot the eigenvalue of this matrix. As I said, so one part, the tactical integral is known. This M1 is known. Both M1 and M2 are known from IBP reduction, and only unknown parameter is this bubble integral. So I have a matrix which depends on just one parameter, and if I plot its 10 eigenvalues, you can immediately see that the vast majority of the parameter space are ruled out because the lowest eigenvalue is negative. So you actually have to zoom in on a tiny region in this plot to see that the lowest eigenvalue actually becomes positive in a small region, which is of the size 10 to the minus 3. Even in this region, this eigenvalue only becomes a little bit positive. And so once you now your now you this is the two-sided bound. This is the precise two-sided bounds you are after. In fact, so the bound is rigorous up to any loss in numerical accuracy, and you can actually make an educated guess of the true value of the integral. And if you maximize this lowest eigenvalue and take this as the central value of your prediction, it actually gets even more accurate than the rigorous bounds. So the rigorous bounds are roughly of the accuracy 10 to the minus 3. But if you take this central value, which maximizes the lowest eigenvalue, you get to an accuracy of around 10 to the minus 6. And so in this simple example, there is only one unknown master integral. So it's very easy to do a one-dimensional scan of the parameter space to get this kind of bounds. But in the general case, there are several master integrals. Mainly, you could have 2 master integrals, 3 master integrals, and in some very demanding problems for Feynman integrals, you can get dozens or even hundreds of master integrals. But so And then the question will boil down to search a multidimensional search in your parameter space to pin down a narrow region in multidimensional parameter space that solve the positivity constraints. And so it becomes impractical to just directly scan the parameter space. And fortunately, in the inspiration I mentioned, for example, conformal bootstrap and recent work on bootstrapping quantum mechanics and lattice models, people have found that the technique of semidefinite programming can solve this problem very efficiently. So,
sorry, before you go on, I do want to ask about this central value thing.
Okay.
So to me, this fact that you can do much better by using the central value is surprising. So it is common, and I want to know if you've thought about this. It is commonly the case, or I don't know, in examples I've seen, it's commonly the case that the true value lies on or near some extreme of the allowed region. Right? So famously, of course, in the conformal bootstrap, but I've run across a similar phenomenon in the quantum mechanical bootstrap. And so the question is something like, do you have any insight as to why the central value might be a good approximation here and not in other places? Or is this just a mysterious thing, a mysterious question we're not allowed to ask?
It's a little bit mysterious, but this central value only becomes so there's also one difference with conformal bootstrap. They are trying to get an allowed region, but in this question, the computed quantity is a precise value. You can approximate to any accuracy you want. It's so we are trying to pin down an isolated point in parameter space. But I also encountered one situation where the actual allowed region is very much near the boundary. That's many slides ago. So it's a very early slide where I write down two ad hoc constraints, and my exact value lies much closer to the upper bound than the lower bound. But for the problems I investigate, once I use a large number of constraints, I get very symmetric plots like this, and the central value happens to fit the actual value of the Feynman integral very well. But yeah, I don't have a very good intuition for this.
I have some speculation that it has to do with the fact that the central value is also the maximum value in this plot. Like in the conformal bootstrap, often if you have an island, one edge, if you go to a higher cutoff, one edge will shrink much more than the other. But I suspect that if you actually had a plot like this of some whatever leftover or something that's supposed to be positive, that you would see that it's not symmetric like your little triangle that you have here.
Okay.
Yeah, thanks.
Okay. Then now I just plot how the error shrinks as my cutoff degree is raised. So the horizontal axis is the cutoff degree of my polynomial, and the vertical axis is the relative error in evaluating this rather simple example of a one-loop massive bubble integral. If I go to a cutoff degree of 10, I can reach very high accuracies. So the rigorous bounds reach an accuracy of around 10 to the minus 12, and my central value actually gets a little bit even better. And as people have seen in other contexts, like the quantum mechanics bootstrap, the convergence is exponential as your cutoff degree is raised. But this exponential convergence actually comes with quite a bit of a computational price, because the computational results doesn't scale linearly as I raise the cutoff degree. So specifically for me, this integration by parts reduction will be quite demanding. And then of course, there's also computational resources used in solving the semidefinite program. But ignoring these questions, you can see that there's an exponential convergence pattern, and which makes you believe that this should, in principle, allow you to evaluate the integrals to an arbitrary accuracy as long as you have enough computational resources. I think the non-trivial statement is just that you isolate the allowed region to really a point or as close to a point as you want, rather than a finite region that doesn't shrink further. I think that's the same observation people made in the quantum mechanics bootstrap, and as you can, in principle, constrain, for example, the ground state energy level to as high accuracy as you want. Okay, and as people have also seen, there are numerical accuracy problems that kick in if you raise the cutoff degree. So if I use the typical machine precision calculations, the exponential convergence pattern fails to hold once I go beyond the cutoff degree of 5. And I have to use double the usual machine precision to continue this exponential convergence. That's similar to what people have observed. And in some later examples, I will also go to quadruple the usual machine precision. And all this is available in the SDPA software. Okay, and as I previously covered the case that the external momentum is essentially Euclidean, p squared smaller than 0. But actually, I can slightly extend the applicability of my method. I can get to any value of p squared smaller than 4m squared, as long as I'm below the Katsky cut threshold. I know that the integral is real valued because the cut doesn't exist and you cannot get an imaginary part. So the real valuedness of the integral becomes manifest if you write down the integral in Feynman parameter space. So if you write down the integral in Feynman parameter space, allowing arbitrary powers a1 and a2 for the propagators, you get an integral from 0 to 1 for the Feynman parameter. The powers of the propagators become powers of x and 1 minus x. And then you get some graph polynomial or semantic polynomial. This semantic polynomial is always positive as long as the value of p squared is below the Katsky threshold. So you get something that's always 0. It never crosses 0 to negative values. So this I epsilon prescription never have an actual effect and can be safely ignored. So you have some manifestly real valued integral, and you can just play the same game here. You can replace this x to some power and 1 times 1 minus x to some power by some arbitrary positive polynomial. And to get a positive polynomial, you just write down any polynomial in x and you square it. And you know this is a positive integral. Once you expand the polynomial into monomials, each monomial can be identified with some power of x and 1 minus x, and so it can be identified with the bubble integral with some values of a1 and a2, and by integration by path reduction, all these constraints become constraints on the two master integrals. So the story that follows is exactly the same as what we worked out in the momentum space representation of the positivity constraints. So once the dust settles in this Feynman parameter space reformulation, you can get highly accurate evaluations of the integral for positive values of p squared, as long as it's below 4m squared. I'll just jump to the plots. and you can similarly get exponentially converging results for your integrals for now with a positive value of p squared. Okay, and now for the time remaining, I'll show you that the epsilon expansion can also be handled in our framework. I will slightly switch gears. So rather than talking about precise evaluation of Feynman integrals, I will tell you that what general features that an epsilon expansion must have to be a valid epsilon expansion. So the message is that the epsilon expansion is not an arbitrary expansion with random coefficients. They are but rather they are internal consistency constraints. So here I will consider an arbitrary Euclidean Feynman integral, which is convergent. So at any loop order. So I consider integrals where there are propagators, which can be raised to any power without numerators. So all such integrals can have very simple expressions in terms of semantic polynomials. There are two semantic polynomials. One is called U and one is called F. In Feynman parameter space, the integrand is just U raised to some power divided by F raised to some power. The exact powers depend on the powers of the propagators. So the sum of those powers A1, A2, A3, etc. is written as A. And then there's the dependence on the loop order L and the dimension D. So so this is D. If I expand D equals D0 minus 2 epsilon, I just the epsilon expansion becomes extra powers of some logarithms of graph polynomials. So the nth power in the epsilon expansion is just the same integral, but with the logarithm raised to the nth power. Okay, now I can get a positivity constraint on this epsilon expansion. Since we are talking about the logarithm raised to some power, I'll just consider positive polynomials in this logarithm. I can consider any polynomial under certain cutoff degree, and if it's squared, then it has a positive integrand. And after integration in this compact Feynman parameter space, you get a positive integral. And so by the same logic we had before, you have some quadratic expression in the monomial coefficients, and that's positive for any free coefficient of these monomials. And so you get the constraints that this you get some matrix must be positive semidefinite. In this case, the entries of the matrix are simply identified with the coefficients of the epsilon expansion. So specifically, I write down a matrix in a very special form, which are called a Hankel matrix by mathematicians. The first row is H0, H1, H2, where H is just some sequence. The second row is still the same sequence, but with an offset, starts with H1, goes to H2 to H3. The third row has even one more offset. It starts from H2 and then it goes to H3, H4. So with this matrix, where each defined where Hn is just a rescaled coefficient of the epsilon expansion, I know that this matrix must be positive semidefinite. For example, if you take any n by n top left block of this matrix, for example, if you just take this 2 by 2 block, then you only look at the zeros order, first order, and second order in your epsilon expansion, and this matrix must have a non-negative determinant, and actually all the eigenvalues must be positive. So this is the generic constraint we have on epsilon expansion. And the constraint is extremely generic. the only assumption is that your integral is finite and it has no numerator. So it's applicable to many classes of Feynman integrals people have evaluated in the past for decades. So essentially, there are decades of data that can be checked against this simple consistency condition, which although it's simple, which seem to have escaped discovery by earlier discovery by people. Okay. So in the time that remains, I'll just show some results for the epsilon expansion for the bubble integral. So this is a generic statement about the epsilon expansion. But if you do the IBP reduction, you can turn such statements into statements about master integrals. And you can precisely evaluate the epsilon expansion for the master integrals. For example, for the bubble integral normalized by the category integral, I can get the epsilon expansion terms also to very good accuracy. I won't have any time to go through the free loop example in any details, but I'll just mention that it's in some way, it's a rather simple three loop example because it's an example with only 4 propagators. If you have some non-trivial scattering amplitudes at 3 loops, usually you are dealing with integrals with far more propagators. Still, the example here is non-trivial because I set all the 4 internal masses to be different and also the external mass to be different. So this kind of integrals have actually attracted a lot of attention for analytic evaluation, but here I will focus on numerical evaluation. There are 11 master integrals that are non-trivial. I will use positivity constraints to constrain an 11-dimensional parameter space, which is why semidefinite programming becomes important for this kind of non-trivial examples. And in the end, I'll just jump to the results. The kind of accuracy I get is also quite good, even for this 3-loop example. So there are here are the results for 3 example master integrals out of the 11 master integrals. So you can see that I reach an accuracy of about 10 to the -9 once I go to a cutoff degree of 6 for some polynomial in the Feynman parameter formulation. If I go to the epsilon expansion, the epsilon 1 and epsilon squared powers, their accuracy are a little bit worse, but still I reach quite good accuracies. And so the computation time is it's not very large. It's the computations are done in a matter of hours. You can see that although the accuracy shrinks exponentially as cutoff degree is raised, the computation time also goes up considerably because the vertical axis is on a log scale. Actually, the IBP reduction time is dominating in my example, but from the plot, it can be seen that if I raise the cutoff degree further, the semi-definite program aspect will likely take over. And for my example, I found it to scale like the cubic power of the matrix size I have. Okay, so in conclusion, I don't have time to go through this. In conclusion, I've outlined a new method for evaluating Feynman integrals using inequality constraints. And I also found new consistency relations for the epsilon expansion of any convergent Euclidean Feynman integral. Here, the method crucially relies on linear identities for Feynman integrals, which are similar to the recursion relations people have used in bootstrapping quantum mechanics. Curiously, this kind of linear identities are also very useful for another method of evaluating Feynman integrals. So that's the method of differential equations. So there are recent work in applying this method to non-perturbative settings like lattice correlation functions cited here. I would say that in the grand scheme, our problem, even our three-root problem, looks rather simple applications, because for Feynman integrals, it's known that the number of master integral is finite. That's how similar to how a finite number of moments is needed in bootstrapping one-dimensional quantum mechanics. I think people have looked at more complicated examples in quantum mechanics beyond one dimensions, or things like matrix models in the large N limit, where the needed moment to start with is actually infinite. But for Feynman integrals, the situation is actually quite tame. And then for future work, it will be interesting to think about ways to go beyond Euclidean Feynman integrals, because for real applications, eventually you also need to deal with Lorentzian Feynman integrals with imaginary parts. Thank you very much.
All right, thank you for giving this talk. Are there any questions? If not, I've got a list, but if other people have questions, go ahead first. All right, can I ask, Mao, do you think you know how to prove that this hierarchy of SDPs actually does converge to a point?
I don't have a good idea, but the intuition I have is that through this procedure of integration by part reduction, if I have a very high cutoff degree, I will get very large numbers here for the powers of the propagators. And I will get very large values for the coefficients of the master integrals, which makes the expression extremely sensitive to the value of the master integrals. So my intuition is that because you get very large numbers in the integration by part reduction of the constraints, if you get the value of the master integral wrong by a tiny bit, you will violate your positivity constraints. But I don't have any idea how to actually prove it. But another speculative idea I have is that when I write down some ad hoc constraints, so for example, here, my upper bound matches my exact result much better than the lower bound. So when I investigate why this actually happens, I find out that the upper bound not only matches the exact results when you, at this point, p squared equals 0, but it also matches the first derivative exactly. And if I write down some more complicated test integrals with higher powers, I found that sometimes you can even match the second and third derivatives and so on. I think with higher and higher powers for this kind of test integrals, you can match higher and higher derivatives around some special points in kinematic space. So there's seem to be some connections with the series expansions, but I don't have any idea how to prove it. But I know this is a quite widely appearing problem also in other contexts, and people It's also a conjecture in the quantum mechanics bootstrap, for example.
Okay, gotcha. Thanks.
I have a question. So in your very last bullet point, well, I guess it's related to that, but first of all, so all of your bounds are basically between master integrals of the same loop order, right?
Yeah, that's right.
So is it possible that there exists some recursion relations between different loop orders, maybe using cutting rules or something like this?
Oh, okay. So in my specific example of the three loop integrals, so if one of the four propagators is raised to power 0, i.e. shrinks to a point, the integral just becomes the product of three tactical integrals with different masses. So these trivial integrals are actually the product of one loop integrals. Yeah, so essentially we are using the product of one loop integrals as my known information to bootstrap the unknown integrals, which are genuinely three loop. And in other examples, you can also have factorizations. For example, a three loop integral can turn into a non-trivial two loop integral times a one loop integral. So I think the way I treat things is linearize everything. So rather than looking this as a one loop integral cubed, I look at this whole product as some known input. But if you look at the problem in a more granular manner, there are factorizations in the problem. So there can be nonlinear constraints.
Okay. Thanks. I'll have more questions, but I'll let someone else go.
Okay.
I mean, I'm just gonna come back, obviously. If so, do you have thoughts about extending this to, well, first fermions?
For Feynman integrals, fermions, it's not a difficult problem because in a perturbative setting, you just evaluate the gamma traces, and once you evaluate the gamma trace, everything just turns into polynomials in your loop momentum. I think that essentially you get some non-trivial numerator because your Feynman diagrams have non-trivial propagators and non-trivial vertices, both of which can destroy the positiveness of your integral. But at any finite loop order, just by integration by path reduction, all these things are with any numerator and any vertices. I mean, things are linear combinations of master integrals. They can come with negative coefficients, but I just need to figure out how to evaluate the master integrals themselves. So yeah, so I entirely bypass the question that the amplitude itself is not positive in this.
For fermions, is there a larger number of? I mean, I know very little about this. Is there a larger number of master integrals due to the fact that you also have an independent numerator, or does it turn out I can relate it to essentially the same set, and so the number of master integrals isn't larger for a fixed loop?
It's actually the same number of master integrals. For example, you can, for fermion amplitude, you can do some gamma matrix projection. You project onto a basis of gamma structures. And then the coefficients of each gamma basis, it's just some scalar integral with no gamma structures. And then, then it's the same IBP reduction again.
So wait. Never mind gamma matrices. I would expect I would have, some monomial of momenta in the numerator.
Oh yeah, that's right. So I didn't make it clear, but the procedure of integration by parts doesn't just work for propagators raised to higher powers. You can also insert any numerator, and actually the numerator can also have arbitrary powers. And the set of master integrals is actually completely unaffected. I mean,
Gotcha. Okay.
it's the same set of master integrals that you get without numerators, but only with propagators raised to higher powers.
Okay, so that's the best news possible.
Yeah.
Almost. It could be there were fewer. That would be even better. But okay, good.
Yeah.
Thank you.
So what would you get out of doing Lorentzian integrals? Isn't Euclidean all you need for any application, or maybe I'm just being stupid?
So I mean, for Lorentzian integrals are very common. For example, in this kind of propagator self-energy integrals, often the things are Euclidean, but if you think about 4-point scattering, like a box diagram, 4-point scattering, I mean, that's above the Katkowski threshold. I mean, that's a very common thing in collider physics or in many other settings. So yeah, I think the real applications I think the Lorentzian integrals are very common. So that's an obvious next question.
I see. Yeah, in the case where there's an imaginary part thing.
Yeah.